Today we have an interesting problem called implement queue using stacks. We have to implement the first in, first out FIFA queue using only two stacks. The implemented queue should support all functions as normal queue, so we have push, pick, pop, and empty. And now we will go through. First, we will go through the difference between uh, FIFA and last in, first out data structure. So this is basically our stack, and this is the queue. So in the queue, once we push, okay, let's just imagine this is the queue. Once we push the element to the back of the queue, we will push it here. So let's say we push 1, or next we push 2, and next we push 3 and 4. Now pop will remove the queue from the element from the top, from the front of the queue. So our first element that was inserted. Peak will also not discard this element, it will just return whatever we have at the front. And the empty function will just return if the queue is empty or not. But in the stack, we have the following. We will place 1 here, 2 here, 3 here, and 4 here. Then if we do pop, the last number that was inserted will be discarded and returned as our result. The same goes for peak. It will not be discarded, but we will just return whatever we have at the top of the stack. So as you can see, this is the reverse order. We have the same order of insertion, like we have 1, 2, 3, 4. But if we apply the operation, standard operation like push, pop, pop, and peak, we will see that we return reverse order. So for queue, we return the same order of insertion, but for stack, we return 4, 3, 2, 1. So we return the reversed order. That's it. This is the hint that will enable us to solve this problem. Now we must, there are some notes. We must only use standard operation stack, so we can just use the equivalent operation that we are asked for. So push from top, peak, pop from top, size, and this empty operations are valid. And also, here's a note that in some languages, the stack might not be supported natively, and we can use a doubly linked list to simulate stack. And now we have an example here, but we just went over the queue, so we know what we are talking about. Now we will go through the constraints. For the constraints, we have the numbers are from 1 to 9. At most, 100 calls will be made to the operation. All the calls to pop and peak are valid, which is also a good question for an interviewer. Are we gonna apply pop and peak on empty queues? Because in that case, we have to either throw an exception or return a default value -1, for example, or with whatever we agree with the interviewer. And then we have also follow-up, and we'll discuss this when we get to the time and space complexity, but we said that can we implement the queues as that each operation is multi-site. So each operation is a constant. In other words, performing an operation will take overall time, even if one of those operations may take longer. And we will see what this means in the example. So now we will go through the example. Let's say this is our queue. These are the two stacks that we can use to mock the behavior of the queue. So let's say we are pushing the first element. So our first operation is push. So let's say push 1. In the queue, we'll just push it here. And let's say we have push 2 and push 3. So it will be like this. Now, we can use one of the stacks to push all the numbers, and that would work for the push operation. We will have the same behavior. So we would push 1, 2, and 3. Now, if you want to peak, If we had a regular queue, we will just return 1. But in our current two stacks approach, we cannot get 1 because it's at the bottom of the stack. We would have to get rid of all the numbers that are before it in the stack to get to the number that we are looking for. In this case, it's number 1. So we kind of have to reverse the order to match the order in the queue. How can we do that? Well, if we reinsert the elements that we currently have in the stack to the other stack, the order of elements will be reversed. And I will show you what I mean by that. So if we delete number 3, take it from the top of the stack and insert it in our stack 2, it will be here. Then our top of stack S1 will be number 2. We take that and we place it at the top of S2. Then we do the same for the number 1. And if we do the peak operation on the S2, no matter how many times, let's say 3 times here, we will get the order of the queue. We will get 1, 2, 3. So peak is working also, and also pop in that case will be working the same. We will be just discarding the elements. So, and for empty, let's just go to empty. We basically just have to check if any of our stacks has elements. If any of the stack has element, that basically means that also in our imaginary queue there will be elements. So we can just check we can just use the empty function on both of our arrays, both of our stacks. Now, why do we call this? I will call this function rebalance. So this rebalance means that I'm taking every element in the S1 stack and pushing it in the S2 stack. We will do this when we have peak or pop operations and the S2 is empty. So we don't have anything to return. So we will do the operation then. So now let's get to the time complexity. In this case, we have all the operations that we need for the queue, so we have a working solution. But let's go to the time complexity. So for push, we will just be pushing the elements. Like if we have 5 elements, we will be pushing elements to the stack. So it will be the same as if we had only pushing to the operations applied to the stack itself. In this case, if we have n insertions, we will have linear time complexity. So we are good on that. But for peak and pop, well, first we will, if let's say in S1 stack, we have 5 elements. And that's our n, so n equals 5. So we pushed 5 elements to the queue, which basically means that we push 5 elements to our S1 stack. Now, when let's say we have 5 times the pop, what would be the time complexity of this? First, we would take all the elements in the first pop. We would take out all elements from S1 and migrate them to the stack S2, and that would take linear time complexity because we have to do it for the number of elements that we have in the number of elements that we have in the stack S1. But any further pop function will only take the time that it's needed to pop an element from a stack, from a regular stack, which is constant. So in total, if we have a sequence of operations, the total will still be in proportion to n. You can call it 2n, for example, if you are, but we can omit the factor. So it will be still linear. When we solve the problem, we will first declare our 2 stacks, S1 and S2. And inside the myQ constructor, we will just initialize them to an empty stack. For push operation, we basically just push to our first stack the element that's given to us as the input as parameter to the function push. Then for the pop function, we will check if our second stack is empty. And if it's empty, then we have to rebalance. And by rebalance, we basically just mean that we will move all the elements that we have in S1 to S2 so we can we can pop or peek the element that's at top of S2, which we will do in the next line. We will just return whatever we have as our top of the stack S2. For peak, we will have the same. We will check if the S2 is empty, we will rebalance, and then we will just peek our second stack. Empty, as we said, we just check the queue is empty if both of our stacks are empty. If either one of them is not empty, that basically means that there are elements inside our queue that we are mocking. Now, the last thing to do is to actually create the function rebalance. And to do that, we will just pop all the elements from S1 inside the S2. And we do that with the while loop until we have as long as we have elements in S1, we will pop them and push them to the second stack. Now, for the time complexity, we already mentioned that in overall, we get linear time complexity, even though the rebalance function takes linear time, but it's only called once, it's only called when we have an empty S2 stack. So if we have n operations of push and then n operation of pop, the rebalance will be only called once at the first pop operation. Then for each of the other pop operation, n minus one operation, you can say, we will just take whatever we have at the top of our second stack.